In this video, we are going to look at potential energy diagrams and how we can look at how the energy changes throughout the course of a reaction. Before we do that, let's just review a little bit about bonds and energy. So if we remember, when two atoms are bonded together, there is this force of attraction. The bond is a force of attraction between the atoms. You have, in a covalent bond, you have a pair of shared electrons, and the nuclei on each side are attracted to that electron. And breaking a bond, because this is a force of attraction, breaking a bond would require energy and therefore would be endothermic. Think of like trying to pull Velcro apart or trying to pull two magnets apart. If there is a force of attraction, which is what a bond is, it takes energy to overcome it. And forming a bond releases energy, and we say it's exothermic. And if you remember from our bonding chapter, you have this potential energy diagram that relates to the formation of a bond. When the atoms are far apart, there's no interaction between them. We say there's like at zero energy. And then as they come closer together, it meets an energy minimum when the bond is made. So this energy is being released, since we're in the negative territory here. Energy is being released when a bond is formed, and it would take energy to pull those atoms apart, and this amount of energy would have to be put in to break the bond. So now remember, breaking a bond requires energy, forming a bond releases energy. Huge, huge, huge topic in our energy chapter. So every reaction that we look at is really going to mostly be a combination of both breaking and forming bonds, even if at first glance it looks otherwise. So if I look at this reaction, hydrogen and oxygen gas coming together to form H2O, at first glance, maybe it just looks like bonds are formed, but actually bonds are broken as well. We have to break apart the hydrogen, the diatomic hydrogen, the single bond between there. We got to break apart the double bond between the O's. And then we can reform bonds, form new bonds to make our water molecules. So you'll notice there's a combination of both breaking and forming bonds. Even if we look at something like the second reaction, zinc and sulfur forming zinc sulfide. If you actually visualize zinc on the particle level, zinc has like millions and millions of zinc atoms all metallically bonded together, and you've got to break up those metallic bonds before it can bond with the sulfur in zinc sulfide. Okay, even sulfur is found as S8 typically in nature. So even if at first glance something seems like you're not breaking bonds, typically every reaction is really going to require some bonds to be broken. And what did we say it takes to break a bond? It takes energy. So every reaction requires some input of energy. And what was that amount of energy needed to start the reaction? Remember what that was called? That was called activation energy. That's why there is an activation energy, because you've got to break some bonds before the reaction can turn the reactants into products. Okay, we can actually plot how energy changes over the course of a reaction. Notice my y-axis is potential energy. Sometimes you can just label that as PE. And I'm not giving actual specific units, but just reaction coordinate is my x-axis. It's basically just the course of the reaction without giving actual numbers or times or anything like that. So you'll notice that first I have reactants. Okay, then there's this little hump that I have to get over before turning into products. If I look at the reaction that's going on, I have diatomic A and B, and as products, they are turning into A bonded to B. So basically, I have got to break the bonds between the A's, break the bonds between the B's before I can bond A and B together. So what happens in between reactants and products is this hump at the top is called the activated complex. It's along the path of turning reactants to products. And it's basically this temporary intermediate or this transition phase where we have not yet made products, but we've broken the bonds in our reactants. It has very high potential energy, the highest along this entire pathway, because it's very unstable. We're not really going to find this state in isolation. If I'm trying to test concentration of things, I'm not going to be able to find the concentration of it. Okay, but why why do I have this upswing here? Is because, as I said, I've got to break the bonds between my reactants. I have this requirement, this input of energy that's needed, and I can actually see how much is needed. And then I get some energy back when I form bonds. Okay, that's going to release energy when I turn, in this case here, into products. So I have some input, I have some output of energy, and overall, if I can figure out how much energy is needed to break and form the bonds, I can actually figure out the net amount of energy that's absorbed or released by the reaction, which we're going to call the delta H, or the heat of reaction for that reaction. Okay. So a couple of definitions. The heat of reaction, delta H, is the net amount of heat or energy absorbed or released by the reaction. The products minus the reactant potential energy can give me this value. So if I come back here, if I actually had values here, if I go across and find the product potential energy and the reactants, I could subtract them and get the net amount of energy absorbed or released. Depending on the reaction, reactants might be higher than products, but the activated complex is always going to be the highest point on the curve because I need an input of energy to break the bonds first. Okay. Overall, the reaction will be endothermic if delta H is positive because it'll overall absorb energy. The products will be higher than the reactants in my diagram. And overall will be exothermic if delta H is negative. If overall the system releases energy and the products will be lower than the reactants. So take a moment, look at these two diagrams and figure out which one is showing an endothermic reaction and which one is showing an exothermic reaction. So if I look at these, reactants, products. If I notice here, the reactants are higher than the products. Overall, I am releasing energy. So this would be exothermic. Okay, if I were to subtract products minus reactants, the products are lower, I would get a negative delta H. And look at this one. Overall, the energy is going up. So overall, this is endothermic, and my delta H would be positive. If I were to subtract my products minus my reactants, I would get a positive value for delta H. Notice that in either way, the highest point on my peak is the activated complex. Because in each of these cases, I still need an input of energy to break some of the bonds. I still need an input of energy to break some of the bonds. It's just in this exothermic one, I'm getting more energy back by forming the new bonds. And in this one, I'm getting not as much energy back when forming the bonds. That's why overall this is endo, overall this is exo. But there is a combination of both breaking and forming bonds in both of these reactions. Okay. We can actually put the magnitude of heat from delta H or even the words heat or energy into the chemical reaction. So remember, something's endothermic, delta H is positive. And if something's exothermic, delta H is negative. Endothermic means heat's absorbed. Exothermic means heat is released. So if heat's absorbed in the reaction, that means heat is required to be there. Heat can be functioning as a reactant. So we can put heat on the left-hand side of my reaction. And exothermic would be the opposite. It would be releasing heat. Heat would be a product. You could put it on the right-hand side. So in these two examples, okay, this first one is an endothermic reaction. Delta H is positive. I could put this value of heat on the left-hand side because it is a reactant. It is required to have 182.6 kilojoules for every 1 mole of N2. So I could put that on the left. I could also sub in the word heat or the word energy if I prefer, but I can actually put this value for this reaction. This is still another way of representing a thermochemical equation. Rather than putting delta H on the side, I can actually put it right into my reaction. Okay, and in the second one, like I said, I could put the word heat, the word energy instead. And the second one, delta H is negative, heat's released, so I can put heat as a product. I can put the word heat or energy, or I can actually put in this value. And if I'm putting in this value, I don't need the negative sign anymore. The negative sign here is telling me it's exothermic for delta H. But if I'm releasing 483.6 kilojoules, I can just put plus 483.6 kilojoules on the right-hand side. I don't need that negative sign anymore because the place right or left is telling me whether it is endo or exothermic. So when I'm putting it into my reaction, I'm always putting it as a positive value, but the side, left or right, is going to tell me whether it's endo or exothermic. Okay. And that's why we can use delta H as a conversion factor, because it really is just another stoichiometric quantity. If I could do a mole ratio of N2 to O2, for every 1 mole of N2, I need 1 mole of O2. Or I can also do this now with heat. For every 1 mole of N2, I need 182.6 kilojoules of heat, because it's actually part of the reaction. It's part of this whole stoichiometry. Okay, another value that we can get from this graph is called the activation energy, and we can sometimes give it the symbol EA. And remember that that's the amount of energy needed for the reaction to occur. If I don't have this energy, the reaction will not happen. And I can get this from our graph if I have the potential energy of the activated complex, that highest point on the graph, and subtract out the potential energy of where I start, the reactants. Notice that even exothermic reactions require activation energy. Okay, it just happens that this energy is lower for an exothermic reaction over an endothermic one. So if I just kind of go back to show you, okay, they all require some energy to get started. The endothermic route just will typically have a higher activation energy than the exothermic route. And that's why systems tend to go toward exothermic pathways, because the activation energy is lower. I need less input of energy to get that reaction started. Okay, so let's show this on our graph. So sometimes you might see a question with arrows or asking you to draw on the graph. We can always show the delta H, the net amount of energy absorbed or released by the reaction, by drawing a vertical line between products and reactants. And I don't care where on the graph it is, if it's over here, if it's over here, if it's over here, as long as it goes from products to reactants. Okay, and we can show the activation energy as the energy needed to get it started. Well, let's see, where do I start? I start at the reactants. How high do I have to get? I have to get over this hill. So the activated energy, or the activation energy, should go from reactants to the activated complex. It's the hill you have to get over from where you start. It's not from the bottom to the top, but from where you start. And again, I don't care where you draw this on the graph, as long as it goes from reactants to activated complex. Okay, and notice the endothermic route is going to the right, is going forward, because overall from reactants to products, my energy goes up. And the exothermic route, if forward is going endothermic, then the reverse must be doing the opposite. Exothermic would be going to the left, reverse direction, and notice overall the energy would be going down. Okay, I can actually write in or show the activation energy going in reverse. And from where I start, if I'm going in reverse, I'd be starting at the products. So the hill I have to get over, the energy input I have to put in, would be from products to the activated complex. So I would want to show a vertical line between those 2 points. And notice why exothermic reactions are favored. Because going forward, look at how much energy I need to put in, the activation energy, compared to the reverse activation energy. The reverse activation energy is so much smaller that typically the exothermic route in this case would be more favored. Okay, that's not to say I can't go forward, but it just requires more energy. So if I have really high temperatures, it might be more favored, and a lot of other different conditions. Another thing that can affect the potential energy diagram is adding a catalyst. And if you remember from kinetics, collision theory, anything that can increase the number of effective collisions will increase the rate of the reaction. A catalyst is something you can add to do that. And typically it will provide a different pathway or mechanism that has a lower activation energy. So a catalyst will lower the activation energy, and therefore you'll have a higher chance of having successful collisions. Sometimes you can have a catalyst, like in this reaction. This is a catalytic. This is actually how the catalytic converter in your car works. It provides kind of a surface for the oxygen to adhere to, and it helps to break the bond between the oxygen molecules. And then if you have carbon monoxide coming out of your exhaust, the carbon monoxide can then bond to this catalyst, which is platinum, and it facilitates the bonding between one of the oxygens from the O2 to the CO and forming CO2. So basically what happens is it's facilitating the bond breaking. It's also creating a more favorable orientation for the oxygen and carbon monoxide. It's giving it a place for them each to bond to, so they're in the right orientation when the oxygen and the CO come together. And a lot of enzymes function in this manner as well. A good thing to remember about a catalyst is that not only are they completely unaffected by the reaction at the end, so they might get used up temporarily, they get regenerated. We said they lower the activation energy, but they don't change the reactants or products. So overall, I have the same reactants. Overall, I have the same product in my reaction. So it actually has no effect on delta H. You have the same products and reactants, so in your potential energy diagram, you'll start and end in the same place, and delta H should remain the same. So if I'm looking at the potential energy diagram, draw the effect of a catalyst, okay? If I draw the effect of a catalyst, I'm starting in the same place. I'm ending in the same place, but the activation energy should be lower. Basically, the hill, that I have to get to from one side to the other, the amount of energy input that I need should be lower. Okay, so without a catalyst, here's my activation energy. Okay, with a catalyst, here's my activation energy. Notice it's noticeably lower. Okay, and if you have to draw this, it doesn't really matter how high the hill is, just still make sure you do have a bump at the top for your, activated complex. And if I look at my delta H with or without the catalyst, products minus reactants is my delta H, it still remains the same. So the delta H overall is unaffected. It is still an endothermic reaction. Overall, my energy is going up, and I should get the exact same value and sign of delta H, whether with or without the catalyst, because my overall reaction is the same. Okay. On the next graph, we're going to do a whole bunch of things. So if you have your note packet in front of you, give these a try. Otherwise, we will do them together if you're watching the video for the first time without a note packet. Okay, so here is a potential energy diagram, potential energy, progress, or reaction coordinate. Label reactants, products, activated complex. So here's my reactants, here's my products, here's my activated complex. Notice that the reaction is actually x2 plus y2 going to 2xy. The activated complex has no bearing on that overall reaction. And this part of the graph is where I am breaking bonds. That's why it requires an input of energy. It is endothermic, or it takes energy to break bonds. And this part of my graph corresponds to where bonds are formed. And then my net amount of energy would be the difference between the products and the reactants. It says to show which way is endothermic, exothermic. This is endothermic going forward because there's an input of overall my energy is going up. Okay, there's an absorption of energy, and the reverse would therefore be exothermic. On the graph, I can show my activation energy. The hill I have to get over from one side to the other. So I start reactants, have to get over this curve. So it goes from reactants to activated complex, and my reverse would be, I'm starting at products, so it would be this hill. Notice it's noticeably smaller for the exothermic route, and my delta H is going from products to reactants. And I don't care where horizontally you're showing that, as long as the lengths of these lines are correct, have the correct starting and ending point. Okay, then it asks for the delta H value. So going forward, products minus reactants, 100 minus 50 is positive 50. It should be positive because visually going forward is endothermic. So make sure your sign matches your visual, double check. And in reverse, now, I would be subtracting 50 minus 100. It is the same exact magnitude, but different sign. It makes sense. I have the same products and reactants, but what was reactants is now products. Okay, same value, different sign. One way will be positive, one way will be negative. Okay, my activation energy should always be positive. Okay, so going forward, it would be 130 minus 50, and I get positive 80. Going in reverse, I get 130 minus 100, positive 30. Notice the exothermic direction should have a lower activation energy, and that's typically why exothermic reactions are favored, more favorable, and more likely to happen, because they require less input of energy. Okay, my potential energy of the activated complex is just from the bottom to the activated complex is 130 kilojoules. It's the highest point on this whole curve. And I can write a thermochemical equation. I have my reactants, I have my products, and I have my delta H. So I can either put delta H on the side of the reaction, delta H equals positive 50, or I can actually put it within the reaction as we talked about before. Positive means it's endothermic. It should be a reactant. It's 50 kilojoules is needed overall to be absorbed in the reaction. So it is a reactant, it's on the left, and I can put it like this instead. Either one of these ways is a correct way of writing a thermochemical equation. And showing the effect of a catalyst, I don't want to change my reactants or products where I start or where I end, but I should have a lower hill. My activation energy is now lower, going both forward and in reverse. They are lower than the uncatalyzed reaction. Okay. Just to mention about multi-step, we had talked about in kinetics that there are multi-step reactions where some reactions are not elementary. They don't occur all in one step, but they have multiple steps. And in a multi-step reaction, there's an activation energy for each step. And remember, we said the rate law, how fast the reaction can go, is governed by the slow step, or the rate determining step, we call that. And so that slow step, what about its activation energy? It must be the highest. It must require the most energy, and that's why it is going at a slower rate, or it's really, holding up the rest of the reaction. Okay. This reaction takes place, so let's look at what a multi-step reaction could look like. Still potential energy versus reaction coordinate would be your axes, which I don't show here. But this reaction would take place in 1, 2, 3 steps. So you kind of have a hump for every step. It says draw the activation energy from each step. So for the first step, where I start to the hill I have to get over would be here. Here's my first activation energy. Here would be my second. From where I start to the hill I have to get over, here would be my second. And my third would be from where I start, the hill I have to get over, right here. And again, I don't care where horizontally you show that. Okay. If you do not have the activation energy, you would not complete the step. The reaction would not happen. Okay. So if I don't have this value of energy, this amount of energy, these reactions would not turn into this intermediate and the reaction would not continue. Okay. Which step would be the slowest based off of this? This has the highest activation energy, so step 2 would be my slowest step of all of these. It would hold up the reaction. If I don't have this amount of energy, I'm stuck here and I can't get over to the other side to complete the reaction. Okay, so let's draw the activation energy for the overall reaction. So overall, it's actually not summing up all the energies. Why? Because here I have to get over this hill. Oh, wait, I get some back. Right? You have to get over the hill. Wait, I get some back. Right? So there is a process. So all you have to do for the overall is overall, where do I start? Here. Overall, what's the highest amount of energy I need up to this point? So my overall activation energy would be here. I don't actually have to add up each step because through each step, I'm putting in some energy, getting some back, putting in some energy, getting some back. But overall, from where I start to the highest point, this is my activation energy. Okay. And at these points, remember, we had said these are where intermediates are present. You might have products that do not appear in each step, that don't appear in the overall reaction, and they would appear at these points, at the end of these steps. Okay, and these top points are all activated complexes or transition states between each of these elementary steps. Okay, and just as a side note, you can have a catalyst that functions in a multi-step reaction, even if the overall uncatalyzed is one step. So if you're drawing the effect of a catalyst, remember we drew just one hill, you can draw 2 or 3 or 4 hills depending on how many steps there are. But overall, the activation energy from where you start to the highest step should be lower than the activation energy for the one without a catalyst.